All right, Newton's law of cooling. That's what we're dealing with today. So basically, Newton's law of cooling states that if you take an object and you place it in a room, eventually the object and the room are going to work itself out to be the same exact temperature. So if you put like a cup of coffee in a room, it's eventually going to cool itself down to be room temperature. So whatever the temperature of the room is what the coffee is going to become. And it goes the other way too. If you set something that's really cold down, it eventually will warm itself up to be room temperature. So they eventually just work themselves out, so they're going to be the same exact temperature. So we have a cup of hot tea is placed in a room. The temperature of the tea is measured every minute. A model for the temperature is given by that equation there. So somebody already figured out the equation for us. That's the hard part. What is the temperature of the tea after 1 minute? Pretty simple. All we have to do is plug in 1 for the little t. So your 56 times your 2.78 to the negative 0.03 times 1, sorry, 0.037 times 1 plus 20. So go ahead and type that in your calculator. Did you get an answer, Seth? Let's go to the nearest hundredth, so 2 numbers after. What do we get? 73 point what? 9. So let's go ahead and figure it out for 10 minutes. So plug a 10 in there. All right, what do we get for 10 minutes? 58.36. Let's go ahead and figure out for 60 minutes. So we get 25.79. So then they want to know, what is the temperature of the tea after 2 hours? Yep, we can't plug in the 2 hours because the formula was used in minutes. So we have to plug in 120 minutes. Do you guys know the shortcut so you don't have to keep typing the whole thing all the time? Yep, second. And then enter brings it back, and then all you have to do is go back and change your exponent from 60 to 120. Oh, I didn't know it does that way too. 20.60. Oh, I've done it before. Like I come to school, I'll make myself like a cup of coffee or a cup of tea, and then I accidentally leave it in the office, and I go and I teach my classes, and then I come back and it's cold. It's not hot tea anymore. So what was the temperature of the tea when you first brought it in the room? So when we first brought it in the room, we had a time of 0, because that's the beginning. That's the first part of it. So let's plug in 0. 2.78 to the negative 0.037 times 0 plus 20. 76 degrees. So if a general exponential is given by y equals a times b to the x plus c, how can you easily find out the starting initial value? Well, we just did what here? We just found the starting initial value by plugging in a 0, right? When I plug in 0 from the exponent, what does this make this whole exponent turn into? Anything times 0 is 0, but then this to the 0 power gave me a 1. So when you added those, you gave a 76. So if we're following the formula, the 56 is your A, the 20 is your C. So quickly finding it, all you have to do is add your A and your C, and that's going to give you your initial value every single time. So instead of having to plug in a 0, you can always just look at those two numbers, add them together. That's going to be our initial. And then what is the significance of the 20 in this question? What do you think the plus 20 means there? No guesses? That's the temperature of the room. So I'm going to go with it. This is in Celsius because 20 degrees is cold. Or their heater broke, and so they're waiting for the person to come fix it, so they made themselves a cup of tea to stay warm. That's my guess. Tea also really helps. All right. So going over half-life again. Half-life of a substance is the time it takes for 1/2 of the substance to decay into another substance. So fluorine 20 has a half-life of 11 seconds. So every 11 seconds, it's breaking down halfway. Write your exponential equation to model this. So our exponential equation to model this, I didn't really give us enough space there. We would follow the y equals a times b to the x power because this is not a question asking us about interest, so it's not one of the other twos. It's always going to be the a times b to the x. So does it tell us how much fluorine we're starting with? Did it? No, up here. Did up here tell us? No. So a is going to stay as a for now. B, since it's half-life, would be 1/2. And then to get your exponent, it's whatever they give you divided by 11, because it takes 11 seconds for it to break down. So you would divide it by 11 to figure out how many times it broke down in the problem. So this is our general formula we would use. So now if we look at the second part, they tell us we have 40 grams. They want to know how much is left after 44 seconds. So those are our two numbers we're going to plug in. So 40 grams would be our A. And then for our exponent, it would be the 44 seconds divided by 11. What do we get? Oh, so 2.5. 2.5 grams is how much would be left. Good old half-life. Look at our last page here. So determining what the growth rate or the decay rate are, sometimes it's really easy. So like these examples, if you have an exponent that's just x, it's really easy to figure out your growth rate or your decay rate. So you have to remember with growth, like this one is growth because it's a number greater than 1. That's how I know it was growth. As we said with our warm-up here, growth is 1 plus the rate. So then if I subtract my 1, that means my rate is 0.04. So as a percent, it would be 4%. Now some people can just subtract the 1 in their heads. That's perfectly fine. If you want to do that, go right ahead. Now the second one though, is that one growth? No, this one is decay because it's less than 1. So decay would be 1 minus your rate is how we got the 0.80. So if I subtract my 1 over, negative r equals negative 0.2. So what would positive r equal? Positive 0.2. So our decay rate would be 20%. How about that last one? Is that growth or decay? Decay. So again, get decay would be 1 minus the rate. So again, I subtract my 1. And I would get a negative 0.05. Divide by negative 1. And rate equals 0.05, which as a percent would be 5%. So those ones, as I said, a little easier because your exponent is an x. These next ones are not so easy because if you look, here this first one I have an exponent of 2x. Here I have a negative x. And there is an x over 4. So what needs to happen is whatever number is with the x, you need to bring that into the parentheses. So like for this one, the 2 would come in the inside, so you're kind of just breaking that exponent apart. You're kind of working backwards from those other rules we've dealt with before. And in our calculator, we need to actually figure out what is 1.04 squared. And that's to the x power. Now, since it's just an exponent of x, we can figure out what our growth rate is. So growth would be 1 plus the rate. Subtract my 1. So what would that be as a percent? 8.16%. For number 5, what are we going to pull into the parentheses to get x to be just positive x? So we got to do 0.80 to the negative 1. And then we still got that x on the outside. So we'll use our calculator. 0.80 to the negative 1. Bless you. So this problem that initially looked like a decay has now turned into a growth problem. So this would be 1 plus the rate. Subtract our 1, so our rate is 0.25. So as a percent, this would be 25%. And then number 6 there, our last one, what are we going to pull into the parentheses? Not just 4, it'd be 1 over 4. There's a 1 here that's not always written, but it is there. So you would have to take the 1/4 away from the x. So 0.95 to the 1/4 power. Seth? 9. Give me one more. For now, yeah, because I told you to go there. Okay. So now this is still a what kind of problem? Decay. So 1 minus the rate equals the 0.9873. Let's see here, 7. Isn't it like 1.227? .9873 minus 1. Negative 0.0127. So then as a percent, we got 1.27%. So then our little box there, all that's doing is that is just saying the same thing that I said up above. Once you have an exponent of simply x, that is when you can figure out if it's a growth or decay and then what the actual rate of growth or decay are.